Our purpose today is going to be to look at some old AP questions from practice tests made by the College Board, the people that write your AP exam. And we're going to focus on Taylor polynomial multiple choice questions and try to figure out the different styles of questions that they might ask. Every time you flip through a test made by them, there are 2 or 3 multiple choice and maybe an entire open response, most likely yes on a BC exam, dedicated to Taylor polynomials or Taylor series or power series, all kind of basically the same thing. So, but this video is going to work on some multiple choice types of questions that you'll see. And what you really need to remember about a Taylor polynomial is that it is for n equals 0, n equals 1, and so on. For each one of those n values, what you need to calculate based on the function is the derivative divided by the factorial times the power. And you've got a more complicated looking formula in your textbook, and that's basically what that formula says, is for each degree derivative factorial power. I just like to remember this because it's a lot easier to remember than trying to memorize that formula. I also like this because in a lot of questions you're not going to need to generate the entire polynomial. You might need to jump to the 4th degree term and figure out what's the value of the derivative given the series or given the polynomial. So we'll see how that plays out in these examples. All right, so we're going to start with one that actually happens all the time on this exam, and that's the shortcuts to knowing the series for e to the x, sine x, cosine x. Those are the big 3. And when you see a series, and this needs to be centered at 0, and it almost always is, then we want to know, and this was, another one of our review topics was our 4 favorite series. You need to start by just writing down what is the series for E. Now this is made by the derivative factorial power pattern by taking all the derivatives, subbing in 0, and using the pattern. But instead of making it each time, we're going to just memorize it for the sake of time. And we only need to get up to the coefficient of x to the 6th, and this will be enough to do that. I'll show you why in just a minute. But, sine and cosine would alternate and have every other term. E is all of the terms, all positive. So if this is the case, then e to the 3x squared over 2, let me just get e to the 3x squared first. What we are doing is literally taking out any x we see and in its place, in parentheses, putting in 3x squared. And the reason we only needed to get to the 3rd degree on our E series is because when we replace that x with 3x squared, we're actually going to be all the way out to x to the 6th at this point. So this is e to the 3x squared. And then let's see, we need to square the whole thing. So this would be 9x to the 4th. And actually, now that I think of it, I don't even really care about that term. What I care about is the x to the 6th term. So I need 3 to the 3rd. Just for the sake of space, I'm going to move it over here. 3 to the 3rd is 27. 27. X to the 6th over 3 factorial. So this is the x to the 6th term in e to the 3x squared, but remember we're doing e to the 3x squared divided by 2, so let me just multiply this by a half to get that 2 from the question. So the coefficient of x to the 6th is 27 over 2 times 3 factorial. And let's see, 27, 2 times 3 factorial. 3 factorial is 6, so that's 27 over 12, and then I can divide both of those by 3 to simplify, and that makes 9/4. All right, so our answer, 9/4. Now, like I said, that's not really, I would put this more in the category of the important series to remember, but it is a type of Taylor series question that you will see, you don't really rely on the derivative factorial pattern, but it is a style of question, and it says Taylor in it, so I wanted to mention it here. Next, this is typical of what you will see as far as Taylor polynomials go. The third degree Taylor polynomial about x equals 4, so that's why all the powers are x minus 4 to that power, is given. What's the value of the third derivative evaluated at 4? So remember, derivative, each term is derivative over factorial times power. So this third degree term, x minus 4 cubed, that's the power part, right? And I'm actually going to move, let me make some space. X minus 4 cubed is the power, which means we need the derivative and the factorial. So the derivative is what we're trying to solve for. The third derivative of the function evaluated at 4, and we need a 3 factorial because this is the third degree term. There's a 3 factorial on it. So the question is, what's the value of the derivative? We know that the coefficient of this term is 1 over 512. So the third derivative at 4 over 3 factorial must equal 1 over 512, because as you were forming this polynomial, that's the term you made right there. All right, so now we just have a basic equation. We're going to multiply both sides of the equation by 3 factorial, and we get 3 factorial, which is 6 over 512. All right, and I don't see 6 over 512, so I simplify my fraction, get 3 over 256. All right, so my answer there, D, 3 over 256. That uses the derivative factorial pattern, power pattern, and that makes that question really quick and really easy. Okay, this one's a little tricky. The 100th degree Taylor polynomial is given. Find the value of the 30th derivative evaluated at 3. So this is the same thing. We just have to do a little thinking to figure out what does the 30th degree term look like. So the 30th degree term is going to happen when n is equal to 15 because of the nature of our general term here. The 30th degree term is going to be the 30th derivative evaluated at 3, which is what we're looking for, over 30 factorial times x minus 3 to the 30th power. All right, that's derivative over factorial times power. All right, all I've done so far, without looking at my series given, is I've used my rule that says the 30th degree term will be derivative factorial pattern. And after, about 3 or 4, we start doing a little number in parentheses to represent the 30th derivative, because 30 little tick marks will not fit. So what that equals is what the 30th degree term looks like, x minus 3 to the 30. Now, if you'll notice, there's no real, other than the factorial, there's no real coefficient. I don't have any numbers up top. This is 1 over 2 factorial, 1 over 3 factorial. Also notice that the factorial is half of the degree. So this term I'm talking about is going to have 15 factorial down here. And then the only other issue is it plus or is it minus? These things alternate. And, I was working this problem and I was thinking, how am I going to figure that out? And there's probably a more elegant way to figure it out, but then I just started counting on my fingers. Is the 30th degree term going to be plus or minus? Well, look at what the pattern is. Let's see, my positive terms are 2 and 6, and I'm counting up by 4s, 10, 14, 18, 22, 26, 30. And I literally did that a few minutes ago. Probably not, there's probably more intelligent ways to figure out that 30 is positive, but that tells me that I have a positive 1 over top of my 15 factorial. Okay, so these two things have to be equal. Remember, my unknown is what is the 30th derivative evaluated at 3. So this equation, I can start by canceling those two. Then I can multiply both sides by 30 factorial. to bring that up to the other side of the equation. And now I'm left with, I know it's a mess, but my answer is 30 factorial over 15 factorial. So kind of similar to this one, just hidden a little bit in there, a little bit trickier version of that same question. All right. Next, we have a Lagrange, or Lagrange probably, error. All right, so basically what you need to know about this is if you read this section in your textbook, it's very complicated. But if you remember alternating series, the sum of an alternating series, like this one, is never more than the next term away from the true sum. So whatever this series converges to, and I know it converges because it alternates, those 5 terms are within 1/6 of the true sum. Lagrange, as far as you need to know, is basically that same idea. What we need to know is that the next term in our Taylor polynomial is our maximum error. And what we do is we figure out what the worst case scenario is on that next term. So Lagrange basically equals, you need to have simple things to think about on your test. You don't want to go in memorizing formulas for something like this. You just want to have the basic idea so that you can get through the problem. You don't need to be real, proper about it. Lagrange is the worst case scenario of the next term. So if I'm going to estimate this value with the 3rd degree polynomial, which tells me right here, then I need to figure out what's the worst case scenario for the 4th term. And the given info will help me out. The 4th derivative is e to the sine x. All right, derivative factorial power. E to the sine x, 4 factorial. So this is the n equals 4 term. 4th derivative, which was given flat out, 4 factorial, and then the power. The power is going to be x minus c. This is the one slight variety here. It needs to be x minus c to the 4th power. The x and the c are 0 and 1. The 0 is the place where we expand. The 1 is the number that we're substituting in. All right. If you got 0 and 1, which usually it'll be simple numbers like that, you're just going to put 1 to the 4th, the difference to these in the 4th. It doesn't matter really which comes first either, because this whole thing is in absolute values. I don't even really want to confuse myself with those. What I need to do is figure out worst case scenario, meaning where is e to the sine x biggest between 0 and 1. And it's always either going to be 0 or 1, whichever one is worse. Sine of 0 is 0. Sine of 1 is sine of 1. So my final answer is going to be e to the sine of 1, because that's the biggest that 4th derivative can be, over 4 factorial times 1 to the 4th. And the 1 to the 4th doesn't do anything. So I need to know e to the sine 1 over 4 factorial. Okay? So let me make sure I'm in the right mode here. I want to be in radians. I can't think of a scenario in your calculator you would want to be in degrees on your test. So go in with it in radians. It might not matter, but more often in calc you're going to be switching from degrees to radians. So anyway, e to the sine of 1 divided by 4 factorial, and that's 24. 2 times 3 times 4 times 1 is 0.0966. Therefore, my answer is 0.097. All right, so just think of it as the worst case scenario of the next term. Plug in either 0 or 1 to the derivative here, and then do 0 minus 1 here to the 4th power. All right, last one. Here's another typical setup that they'll give you. They will give you an expression for the derivative, right? If you're going to go through and form a polynomial by derivative factorial power, they might not just give you a function and say calculate all the derivatives. They might give you a function for all those derivatives. So I want to plug in 0, 1, 2, and 3 into that function and see what I get. For the sake of time, I'm going to speed that up a little bit. If I plug in 0, I get 1/2. If I plug in 1, I get negative 1/3. If I plug in 2, I get 3/16. And if I plug in 3, I get negative 1/10. All right, so make sure you get those if you sub in 0, 1, 2, and 3. I just don't want to take too much time on this video. Now, those are my derivatives. So now, theme of the day, derivative, factorial, power. If we're centered at 0, all my powers are just x to the 0, x to the 1, x to the 2. And I was going to use these derivatives to form my series, my polynomial. So 1/2, technically it's over 0 factorial times x to the 0, but neither one of those two things show up because they equal 1. Minus 1/3 over 1 factorial doesn't show up, times x to the first power. Plus 3/16 is the derivative, 2 is the factorial, x squared, 1/10 is the derivative, 3 is the factorial, x cubed. So we have 1/2 minus 1/3 x, which narrows it down to a couple options, B or D. 3/16 over 2 factorial is 3/32. 1/10 over 3 factorial is 1/60. Final answer D. All right, so Taylor polynomials, named after my great-great-uncle Brooke Taylor. They're intimidating from time to time, but the questions that you will get asked on the AP exam, not as bad as they may seem. Young, Seth Taylor Young, out.